Morning to you all. Today we are going to discuss about a new experiment. The name of the experiment is air wedge. We are going to study what is air wedge. So as we are in engineering physics laboratory for first year, first semester, as we know the subject code is UDPH-CPA, subject code for engineering physics, UDPH-CPA. So we are studying for non-DG courses. So totally we are having a 12 experiment. So each cycle consisting of a 5 experiment. In addition to these 10 experiment, we are having another 2 experiment is added as the value added experiments. For today's class, we are going to consider experiment number 5. So this experiment number 5 is the air wedge. So we are started the second experiment. We completed torsion pendulum to find the rigidity modulus of the given material. Now we are going to study the experiment by which we are going to measure the thickness of the given material. To measure the thickness of the given material, here we are going to consider the experiment is called air wedge. Thickness of the given material. Somebody may ask, sir, by using the vernier caliper alone, by using the screw gauge alone, we can measure the thickness of the given material. But here, why we are going to consider this experiment air wedge to measure the thickness. So by using the vernier caliper and by using a screw gauge, we measure the thickness of the material in macro level. Macro level means we are going to consider the huge object. For that huge object, we are measuring the thickness. For example, we can consider a wooden scale. We can consider a thin wire, or we can consider a rubber. So the material with the huge size are measured with the help of the vernier caliper and screw gauge. But in our experiment, for today's experiment, in air wedge, we are going to measure the thickness of the given material. That material should be in the range of micron level. Micro level materials are going to be measured with this air wedge experiment. Micro level means what, sir? The micro level is nothing but we can consider a paper. We know the size of the paper. How thickness is it? So we can measure the thickness of the paper. Or we can consider our hair. We can consider our hair. We know how thickness is our hair. So that thickness we can measure with the help of this air wedge. So with the help of this air wedge experiment, we are going to measure the thickness of the given material in the micron level. So the micron level we are going to study here. So this is the main objective and the importance of this experiment air wedge. Thickness, it should be in the range of micrometer. So that we are going to measure by this experiment air wedge. So the objective or the aim to determine the thickness of the given material using air wedge method. What is this air wedge? Air wedge. Wedge is nothing but gap. So we are going to induce a fine gap. We are going to create a micron level. So that micro level fine gap that should be created in between these two glass. So yes, from this illustration, from this figure, we can able to see that we have taken two glass plates. We can able to see the colors of the glass plate here in the blue color. So we have taken a two glass plate of a same property. The same property is the same thickness. The made is also by the same material. So we have to consider the two glass plates which obeys the same property. Then we have to place these two glass plate one over the other. We have to place the two glass plate one over the other. One end of the glass plate is tied tightly with the help of the rubber band. One end of the glass plates are tied with the help of the rubber band. So we have to tie the rubber band. Sorry, we have to just tight these two glass plates with the help of the thread or the rubber band. If we tight these two glass plate with the help of a thread or the rubber band, we can visualize, we can see that there will be no any gap. There will be no any gap. So now on the other hand side, we are going to consider our test specimen. For example, if I am going to consider the small paper piece, so I have to insert that paper piece at the free end. So the one end we have tied with the help of the rubber band or the thread. On the other hand is the free end. So on the other hand, free end, we are going to introduce the paper, fine paper. So by introducing a fine paper that we have shown here in the orange color, test specimen. So by introducing this test specimen on the free end, we can able to induce a small gap. We can able to just say that we are able to see that a small micro level gap takes place in between these two glass plate. So these two micro level glass plate is nothing but air gap. So the air gap is called as air wedge. So this is our experimental name. We have to know what is air wedge. Air wedge means air gap. How we are going to create this air gap? So for to create this air gap, we have to consider two glass plate of a same property. Place the two glass plates one above the other. When we place the glass plate to overlap with each other, there will be no any gap. So the one end of the glass plate is tied tightly with the help of the rubber band or the thread, so that there will be no any gap between the two glass plate. Once we made the one end of the glass plates to be the fixed one, on the another end, it is a free end. In the free end, we are going to introduce our test specimen. We can consider hair or we can consider paper. So here I have taken a paper. Test specimen is the paper, fine paper. So once we introduced the fine paper on the free end, we can able to visualize that a small air gap takes place in between these two glass plates. So that air gap here called as air wedge. So this is our consideration. After introducing the test specimen in between the glass plate. Once the gap takes place, once the gap is created, then we have to place this entire setup in front of the monochromatic light source. When the monochromatic light radiation falls on these glass plates, from the top surface, it will goes to the intermediate region, the air gap region. Then it falls on the bottom surface. Again, when it strikes the bottom surface of the glass plate, it reflects back. So the transmitting ray and the reflecting ray, they will overlap with each other. They will interfere with each other. As the result, we are able to see the interference pattern that I have shown here in yellow, black, yellow, black, yellow, black color. So here we can able to see the alternative fringes, fringe pattern. So this fringe pattern is the band width. This fringe pattern is the lines. So here we are going to create a lines. That lines are even. Alternatively, we are having the bright, dark fringes. So these are our experimental result. The air wedge experiment is very simple. We have to know the mechanism. We have to know the procedure. So whenever you are going to do this air wedge experiment, when you are entering inside our physics laboratory, when the students are just doing this experiment, first they have to consider the two glass plate. You have to ascertain that whether the glass plate having the same thickness or not. If the thickness of the glass plate is differs, so you have to change the glass plates and you have to make the glass plate to be same thickness. Once the glass plate is considered to be an equal glass plate, then place the glass plate one above the other, fix the ends properly. The glass plate end should be fixed properly. Then with the help of the rubber band or with the help of the thread or with the help of the tape, we have to tighten the one end of the glass plates. So once the one end of the glass plate is completely sealed, then on the other end is the free end. So here you have to introduce your test specimen. You can consider a micro level material, paper or a fine hair. So once you introduce the test material at the free end of the glass plates, you can able to create a air wedge. So this air wedge is the air gap. Then we have to place this entire setup in front of the monochromatic light source, and we have to make the light radiation to falls on the glass plate that we have mentioned here in the yellow arrow mark. So once the light falls on this glass plate, then the light undergo transmission and the reflection. So these are transmitted and the reflected ray are superposed with each other, and as a result we are going to get this interference pattern. So that interference pattern we are going to observe with the help of the traveling microscope. So with the help of the traveling microscope, we are going to observe this interference pattern. So this is our experiment. So this only we are going to see by this class, from this class. So the learning objective. As I informed that we are going to measure the thickness of the given material. The material should be in the size of fine microns. So it is a simple interferometer. It is a simple interferometer. Why we are calling this air wedge as simple interferometer? Because interferometer is the medium which makes the two wavefront to superimposed with each other. So here that only we are doing. We are passing the monochromatic light radiation over the glass plates. So the monochromatic light radiation falls on the glass plates, then it will reflect back and they superimposed. As a result, we are obtaining the interference pattern. So that's why this experiment air wedge is also called as simple interferometer. So in simple interferometer, we used to visualize the disturbance of the wavefront after propagating through a test object. So this is our learning objective. Other than this learning objective, we can measure the interference pattern. We can calculate the bandwidth of the interference pattern. So these are experiment. We are going to measure only the bandwidth. The bandwidth here, it's given by the symbol beta. Beta. So the symbol for the bandwidth here, it's beta in the formula. So the beta only we are going to measure. The bandwidth is measured only after the occurrence of the interference pattern. So you have to form this interference pattern. Then only we can able to measure the bandwidth. So to measure the length of the air wedge, we can measure the total interference length also to determine the thickness of the given material by using the formulas. So this is our learning objective. It simply called as interferometer. In interferometer, we are going to visualize the disturbance of the wavefront. We are going to form an interference pattern. With the help of the interference pattern, we are going to calculate the bandwidth beta. So this is our experiment. So the apparatus required to do this experiment, we have to consider the optically plane glass plates. The glass plates should be highly transparent. Why we are considering the optically plane glass plate? Because then only the light radiation will penetrate through the material without loss. So we have to consider two transparent glass plates. Then we have to consider a traveling microscope. So with the help of this traveling microscope only, we are going to measure the bandwidth. Then a fine wire. So this fine wire is the test specimen object. As I informed, we can consider a piece of paper. We can consider a piece of thread. We can consider a piece of silk wire, or we can consider our human hair. So these are all the test material. Then we are going to consider a lamp. Here the lamp is a sodium vapor lamp. So the sodium vapor lamp, we know that it is a highly monochromatic light source. By this sodium vapor lamp, we are going to get yellow color. So that yellow radiation falls on the glass plates with the test specimen. This yellow radiation will be reflected in the traveling microscope as the interference pattern. Alternatively, yellow, dark, yellow, dark, yellow, dark. That yellow color is only due to the presence of the light source. I am using the sodium vapor lamp. That's why the outcome color is in the form of a yellow. Then a reading lens. To measure the readings in the traveling microscope, we are going to consider a reading lens. Then meter scale. So this meter scale is to measure the distance between the edge of contact and the specimen in the glass plate. So in the glass plate, we are going to measure where we placed the specimen. So from the rubber band end, or from the thread end, or from one end to the another end, we have to measure the length. That length is measured with the help of the meter scale. So these are all the apparatus required to carry out this experiment. We need a plain glass plate. We need a traveling microscope. We need a test object. We need sodium vapor lamp. We need a reading lens. And finally, we need meter scale. So these are all the apparatus, what we have just seen in the last slide, that I have visualized here. We are going to consider the glass plates. Here the glass plates are optically plane transparent glass plate. See, we can consider two different size of the glass plates. Here it's the length is increased. Here the length of the glass plate is decreased. So the whatever the glass plate, but that glass plate should be equal in their property. The two glass plates should be equal in their property. That we have to confirm before doing this experiment. So on the other side of the glass plates, right hand side, we can able to see that a person is holding the two glass plate in his hand. One end of the glass plate is tied with the help of the rubber band. So on the other end, he introduced a specimen. Once small air wedge is created, air gap is created. So this is the just a tied glass plates. Then the lamp we are using here is the sodium vapor lamp. So we are not going to pass the sodium vapor lamp directly over the test material. So the sodium vapor lamp is placed inside the box. So here we are having a fine just a hole in the box. We can able to see that fine hole in the box. So through this just a fine hole, the intensity will exit out. That intensity fall on the test glass plates. So the sodium vapor lamp is the third consideration. Then the reading lens to measure the readings. And the final apparatus, the main part is the traveling microscope. So with the help of this traveling microscope, we are going to measure the bandwidth. So to measure the bandwidth, we are going to consider this traveling microscope. So this is the image of this traveling microscope. Here in the traveling microscope, we can able to see that we are having a two scale. One is a horizontal scale from our head to the toe. If the person is standing, we can consider our head and we can consider our toe. So this is the vertical scale, top to the bottom. Horizontal scale is from our left hand side to the right hand side. Left hand to the right hand side. It's the horizontal scale. So here with the help of these scales only, we are going to measure the readings. Then a movable screw. So in the vertical scale, we are having a movable screw. If we rotate this screw, we can able to see the scale value will changes. Similarly, we are having another one movable screw in the horizontal scale side. By rotating this screw, we can able to see that the entire session is moved from left side to the right hand side. Then an eyepiece section. So by this section only, we are going to find the bandwidth. So here we have to place our eye side and we have to adjust the just a screw in the microscope. So by doing the fine adjustment here in the microscope screw, we can be able to catch the interference pattern. The interference pattern are observed with the help of this screw by rotating the screw in the downward direction or in the upward direction. So the rotation has to be made by seeing the eyepiece section. So this is the just apparatus we have considered in the microscope, traveling microscope. And finally, I have placed on meter scale also. So here this meter scale is used to measure the distance between the edge of contact and the specimen that we are going to see in later. This is the experimental setup, experimental construction. So whenever we are writing our record notebook, we use it to draw a structure like this, a simple form of the explanation, simplest way to explain the construction. So from this diagram, we can able to see that we are having a source. Yes, is the source. Here the source is the sodium vapor lamp. So from the source, we are going to produce the monochromatic radiation. So the monochromatic radiation is falls on the 45-degree inclined glass plate. we are going to place the glass plates. Here we are having that glass plates, transparent glass plate L1 and L2. So these transparent glass plate L1 and L2 are placed inside a wooden stand. Actually, we are going to place these glass plates L1 and L2 inside the wooden stand. So that wooden stand are inclined at an angle of 45 degree. The wooden stand inclined at an angle of 45 degree. Why, sir? Why we are placing these two glass plates L1 and L2 inside the 45 degree inclined glass plate? Because our ultimate aim to find the interference pattern, to find the thickness, to measure the air wedge. So by directly placing these two glass plates in front of the light source, we are not able to observe the interference pattern. So to make that interference pattern, we are placing these two glass plates L1 and L2 in between the glass stand, which inclined at an angle of 45 degree. So this entire glass stand is then so placed in front of the light source. Now the light radiation falls on the 45 degree inclined glass plate. Then it will pass to the glass plates L2 and L1. Then it will reflect back. That transmitted and the reflected image or the superimposed of the traveling microscope. So that's why at the traveling microscope end, we are going to see the interference pattern. So this is experimental procedure. Source, the light source falls on the 45 degree inclined glass plate. So this inclined glass plate is nothing but just a stand. Then the light radiation falls on the test materials. Then it will reflect back. So the transmitting and the reflecting image creates the interference pattern that we can able to visualize here in the eyepiece section. So the what just we have studying here, that only I have mentioned here in the additional diagram. So here we can able to see that the two glass plate, upper side glass to air boundary, glass to the air boundary. The upside we are having a glass. So in between these two glasses, we are having an air boundary. So in the bottom side, we can say that air boundary to the glass plate, air boundary to the glass plate. The gap between these two glass plate is nothing but air wedge. The light radiation falls on these two glass plates, then it will reflect back. So when we visualize these changes, we can able to see that an interference pattern is obtained. So that our ultimate result. So this is a laboratory setup. Whenever you are coming to laboratory, you can able to see a setup like this only. Sodium vapor lamp. The lamp is placed inside the wooden box. So we are going to switch on the sodium vapor lamp. When we switch on the sodium vapor lamp, the light radiation comes out in all the direction. So we need a radiation to falls on a particular direction. So in that particular direction, we have placed our test material and the traveling microscope. Sodium lamp, then a traveling microscope, then a glass plate in a wooden stand inclined at a 45 degree. We can able to see that the wooden stand is here. So inside this wooden stand only, we have placed the glass plates. The stand is inclined at an angle of 45 degree. So when the light radiation falls on these 45 degree inclined glass plate, then it will reflect back like this. 45 degree inclined glass plate, then the light reflect back, then it falls on the material, then it will again just come out from these materials, glass materials, and it will induce the interference pattern. See, we can able to see that. So the apparatus which we are used here in laboratory. So this is a formula, experimental formula. Experimental formula is very simple. T is equal to lambda L by 2 beta. Very simple. T is the thickness of the given material. Lambda, as we know, lambda is the wavelength. Lambda is the wavelength. Wavelength of the light source. We are using sodium vapor lamp. So the sodium vapor lamp wavelength value is 5896 or 5893 Armstrong unit. So the lambda is constant here. L is the length, actually, that I will explain what is L. Beta is the mean fringe width. The mean fringe width beta, we are going to measure this value only after getting the interference pattern. Once the interference pattern is obtained, then we are going to measure this value. So the formula is simple. Lambda L by 2 beta. Lambda is the wavelength of the light source. L is the length, actually length between the rubber band end to the specimen. The in-between length rubber band to the specimen is L. Beta is the mean fringe width, average bandwidth. This average bandwidth is measured after the occurrence of the interference pattern. So experimentally, we are going to find only the value beta. Other values are a direct measurement, constant also. So this is the experimental way, beta to measure. So this is the just experimental view. Here I have shown the obtained interference pattern. Experimentally, we are going to measure a bandwidth like this only. Whenever you are doing this experiment in the laboratory, you can able to see the outcome is in the form of this interference pattern. Yellow is the light source. The black is the gap. Constructive and the destructive interference. We have studied in the second unit. Constructive and the destructive interference that we have shown here. Alternatively, we are having a bright, dark lines. These alternatively bright, dark lines are called as the interference pattern. It's called as interference pattern. So these only we are going to observe. The reading calculation method. So the reading calculation, how to calculate the reading. So the distance, already I have said that we have to measure the value of a L. The value of a L is measured, we can able to see that. Here we are having just a rubber band or the tape end. So from this end to the specimen, we have placed a hair here, human hair here. So in between these two is the L. So this experimental just way. I would like to stop up to this. In the next class, we are going to see the same one, and I will explain how we have to measure the readings by using the traveling microscope. So if you have any doubt, you can raise your doubt now. Is it clear? Is the procedure is clear?
Yes, sir.
Okay. I have explained only the procedure. I never said how to measure the readings, how to calculate the readings. That we are going to see in the next class. If you have any doubt, you can ask your doubt now. Having any doubt?
So what is that green area? That parallel lines.
Yes, that parallel here, the parallel line which they have mentioned is the actually the band, the distance. See, you can able to see here the yellow line. No, yellow black line.
Yes.
Yeah,
Yes, sir.
actually what they have shown there in the green line, they have shown the order. They have mentioned the order. See, you can place anywhere. You can place anywhere in the obtained interference pattern. So that line you have to consider as an nth line, starting value. Then with the help of the micrometer screw, you have to rotate the telescope, move the telescope, and we have to fix the horizontal crosshair or the vertical crosshair in the band. So the distance between these two bands they have mentioned there in the green color. You are able to see here the lines. I have started here as a 1. This 1 is the first reading for me. Then I am rotating to the fifth line. I have mentioned as n plus 5. So for 1 I am going to take one reading, and then for n plus 5 I am going to measure another one reading. The distance between these two I have to calculate. You can able to see here. For n I have measured as a 5.5. For n plus 5 I have measured as 5.6. I have just substituted the data, obtained data, and I have measured a total reading also. So from this total reading, I have given the difference. The difference between 5 band, n to n plus 5. You have to subtract these two value, first two value. 5.527 minus 5.635. Write the difference here. The difference is 0.108. Then divide this value by 5. Then we get a beta. So that only we have shown here in this green color. The difference between the two bands, two order, n to n plus 5. Is that clear?
Yes, sir.
Yeah, I will explain in detail in the next class. I never started the calculation method. I never said anything about the calculation. Just I have given the procedure, how to just handle the instrument and how to do the setup. That only I have given right now.
Okay, sir. Okay.
Okay, any other doubt?
No, sir.
Okay, then we wind up our class.